Awesome. Hi, everyone. Really great to be here today. So our presentation will be about content security policy. This is Michele. I'm Lucas. We both work at Google in Zurich. We're a part of a special focus area that deals with promising mitigation techniques and proactive projects to mitigate whole classes of bugs. And content security policy is actually one of them. And we spent a lot of time the last year on content security policy. We learned a lot, and we wanted to share some of that with you guys. So, very brief recap before we start. I just wanted to ask you guys, who of you has worked with a content security policy before, even like audited or put it on the site? Cool, some people have, awesome. Who of you know what the nonce-based policy is, like with nonces or with strict dynamic? One? Okay, two. So I think it's very good to have a recap and briefly repeat what happened the last 9 months. Sorry, was that me? No. So basically, we have been here already last year, and we were mostly talking about how to bypass whitelist-based CSPs. We did a pretty big research on all content security policies we could find in the Google search index, and it turned out that most content security policies were used for mitigating XSS, which makes sense because this is why we have CSP mostly, right? In addition to that, we also evaluated the security of these policies, and it turns out that at this time, almost 94% of the whitelist-based policies were completely bypassable automatically, like all the policies from the web, right? Which is pretty bad if you think of it, right? It takes a lot of time to come up with a whitelist-based policy, to refactor your application to make it work, and then you're actually getting not really a lot of benefit. So we actually propose to use nonce-based policies instead of whitelist-based policies because they can offer significantly more security guarantees. And in addition to that, we also proposed strict dynamic, which went into the CSP free spec recently, which kind of makes the nonce-based policies actually workable in practice. So if you want to learn more about like this previous research, like why whitelist-based security, whitelist-based CSPs are not really great, there is a really cool paper we presented at the CCS in Vienna last year, provides a lot of information on that. So, brief recap, how do nonce-based policies work? Basically, you have a content security policy like that. You restrict the scripts that can be loaded, and you have a nonce with a random value. This value needs to be random for every response, right? So the idea is the browser only executes script tags on a site if the script tag has a nonce attribute that matches this random value. So an attacker who found an XSS vulnerability cannot inject a script tag without knowing the nonce, right? And since he usually does not know the nonce, the browser will just refuse to execute the script. So this is the basic principle. In addition to that, nonce-based policies also have the big advantage that you don't have to come up with an application-specific whitelist, which can be a very tedious task if it's a big application, right? And these whitelists often even change over time, right? Which is like a big source of breakage. And yes, in addition to that, you also don't have to care about like whitelist bypasses like JSONP or Angular bypasses for whitelist because it's a nonce-based policy. So how does this usually work? If you take this example, we have like a script with a nonce. This random nonce value is the same as in the policy, so the browser allows this inline script and this source script to execute. It's all client-side, right? If you have an attacker and he injects a script tag, inline or sourced, it does not have the nonce attribute, so the browser says, no, this cannot execute. The XSS is kind of mitigated. So strict dynamic basically builds on top of that. It allows to dynamically propagate trust from nonce scripts to child scripts with basically DOM-based APIs like create element and append child. This is very important because many libraries, JavaScript libraries, create dynamically JavaScript to, for example, for module loading or for JSMP and for this kind of stuff, right? So they don't propagate the nonce, so they kind of break if you don't have strict dynamic. So this is kind of a stepping stone to make this work till most of the libraries have been refactored to, propagate the nonce manually. In addition to that, if you have strict dynamic in the policy, it also drops the whitelist. So if you have, for example, like a policy like this, and then here like google.com, strict dynamic would cause google.com to disappear because if you would have google.com there as well, it would mean that a script could load if it has a nonce or is sourced from google.com. And we want to have it more strict, so we drop the whitelist. This is also very nice because then the policy is backward compatible, which I will show you in a second. And you can use the same policy for older and newer browsers, regardless if they support strict dynamic or not. So this is an example. The top green box is basically what is allowed by strict dynamic. The parent script is nonced, and since there's strict dynamic, it can create a new script and can do append child, and this new script will also be allowed to execute. As I said, this pattern is very often used in libraries. On the other hand, parser inserted stuff like document write or inner HTML is not blessed because that's usually a very big source of XSS. So that was the recap. I want to share some of our experiences with like deploying strict CSP at Google on many big products. It's actually really cool because in the last 9 months, a team of about like 4 full-time equivalent people were able to roll out a strict CSP to like almost 1 billion users. And in total, like so far in 9 months, like 150 services, which is really a lot, right? Because with the whitelist-based approach, you usually needed something between like, I don't know, 3 or 5 people for 2 years to refactor the application, to come up with the whitelist, to maintain it, right? And with the nonce-based policies, this is actually much simpler. So it scales very well. And in addition to that, we're also monitoring CSP violations which we're receiving, right? Every time the browser blocks something, it sends back a violation report to let the developer know that there might be something broken, right? So per day, we receive about 50 million CSP reports. It's a lot, right? So it either means like all our applications are broken or that there's a lot of noise. So like spoiler alert, it's all noise. And this is actually a big problem for us because it makes it really hard to find out if you have some real breakage or if it's just, noise. But we have a slide about that as well later. So a couple of services you may know that have the strict CSP already deployed are Google Photos, Google Plus, accounts at google.com, passwords at google.com, like the sensitive domains, and many more. So there's a couple of requirements that need to be met to actually roll out CSP at that scale. And we wanted to share these with you. Maybe that's also useful for if you want to roll out CSP at your company or privately, right? So what really helped us a lot is baking strict CSP into the core frameworks, right? So that all new services that are built on the core frameworks will have it by default without the developer having to doing anything. And the existing services built on the core frameworks could be opted in after they have been tested by just switching a flag. So this was the case for Google+. We just had to switch a flag to get strict CSP enabled, and it worked, right? Which is really nice compared to whitelist-based policies because it takes a long time to get them work for almost no benefit. So the culprit is here that there's some requirements for this to actually make CSP deployment that easy. And the probably most important one is that you have to have like a service-independent CSP. like one CSP that you can use for every service. And that's actually a nice thing about nonce-based CSP with strict dynamic. You can use the same CSP for all products, not even restricted to Google products, right? You can use that in general, which is really nice. The next thing is conformance tests. You probably have not heard about that before. This is some special tests we run at Google to kind of prevent developers from submitting anti-patterns to the code base. And one of these conformance tests actually check that there is no inline event handlers in the HTML markup. And this was already here before we rolled out CSP, right? And it was very handy for us because CSP does not really work well with inline event handlers. So we did not have to refactor these applications because there were no inline event handlers, which is really great, right? Otherwise, you probably have to go through the templates and refactor them out into the JavaScript registered event handlers, right? Which is, depending on the application size, usually a little bit more work. And third, also very important, we use templating systems at Google that allow auto-noncing of scripts. I have a separate slide on that, but a very prominent one is Closure templates, which is also open source. And the TLDR is you can basically pass the nonce value for the response that you also use for the header at the central place to a templating system, and the templating system nonces all the scripts automatically for you, and you don't have to refactor a single HTML page, which is really handy. And of course, you need monitoring tools and other tools to support this rollout. So this is basically the policy we use almost everywhere. As I said, this is not restricted to Google, but it is really nice compared to these whitelist-based policies. These strict nonce-based policies are kind of always look the same. The only thing you have to ensure is that your scripts are nonced and that you don't have inline event handlers, for example, right? So the nonce scripts work, dynamically created scripts will work. I will talk about this in a second. And we have fallbacks, unsafe inline and HTTPS. If you have an old browser that does not understand strict dynamic, like Edge, then it will just ignore this and will just execute that. And the CSP is basically a no-op, but it will also not break your site, which is probably very important, right? Firefox or Chrome, who understand CSP3, they will drop unsafe inline and they will drop the whitelist. So for them, the effective policy is actually a very useful secure policy. And it's also very important, we have to add object source none and base URI none to prevent other sort of bypasses, which is usually not a problem for most applications. Closure templates. So there's a lot of, there's a bit of magic here, and I'm a really big fan of closure templates because they really make my life significantly easier. Basically, it's like a very simple templating language. You have parameters which get inserted here. Also very important, it has like auto-escaping. So it knows when user input goes into like script tags that it has to escape it for a script context, right? If it goes into like HTML tags, then it knows that it has to escape it for the HTML context, which is very important, right? And on top of that, Closure also works very well with CSP. So there's an example event handler. You don't have to understand the code, but it basically generates a random nonce. And this random nonce is set in the CSP header, and it is also passed as metadata to the templating system. You can do this like in one base handler, like in one central place, right? Not for every template. And then the result is actually very nice. It is, you have basically every script nonced, although you have like no nonce in the template, right? The templating system completely takes care of it, and your site doesn't break because all the legit scripts have nonces, and the user input is escaped properly for the right context. Which is important, right? Because like if you nonce a script and you have unescaped user input here, that could be that could still trigger an XSS then, right? So ship it, right? All good, awesome. So problem is you maybe still break some functionality, some edge cases or something, right? Maybe there was an inline event handler which you forgot. So you basically need to roll out the policy in report only first and look at the violation reports that are sent back from the browser. So in theory, that sounds good. In practice, you will get, like, for big products, like 10 million of CSP violation reports, right? And it's like, oh my God, everything is broken. But it turns out that most of these reports, or almost all of these reports, are actually noise. And the problem so far is that you cannot really distinguish between the noise of actual breakage, the violation reports of actual breakages and violation reports triggered by browser extensions. So CSP3 has a really nice thing for that. It's a new keyword, it's called report sample. And it basically, when the report sample keyword is present in the policy, it basically instructs the browser to send, like, the first 40 bytes of the script that was blocked in the report back to the server. And with that, you can usually learn a lot about the blocked script, right? And you can usually find out if it was a extension or not. Firefox has something like that already for a very long time, although not for event handlers. And the new script sample kind of adds the whole thing to the spec and also covers inline event handlers, which is nice, because then you would have, if you don't have that for inline event handlers, you have the same problem again. You don't know if the inline event handler was there in the first place in your application or if an extension injected it. So this will be hopefully part of Chrome 59. And I just want to show you a brief example about the violation reports, how they usually look like. The first one here is, like, you know, a normal inline script, and the developer forgot to add a nonce. So it will be blocked, and the browser will send a CSP report. I'd say unsafe, like blocked URI inline, the document URI, and it was a script source. Okay, you can deal with that, right? Very similar for event handlers, right? You have an inline event handler on load loaded, CSP blocks that, you get a report. It actually looks exactly the same as the previous report. As a developer, it's not optimal, but you know you have some breakage on your side and you probably have to find it. So the real problem is now extensions. They inject inline scripts like that, and they also inject inline event handlers like that. And if they do so, the browser will also send a violation. And the violation looks exactly the same as the other ones. So as a developer, you get like 1 million reports, like 99.9% are from Chrome extensions, and it's really hard to, I mean, you don't know if you have a breakage or not, right? You always have this ground noise. So 3 different causes of violations yield exactly the same report. With the script sample keyword, this is different now. If you add this to the policy, you also get like the first 40 bytes of the script that was blocked. And this is actually really handy, because you then can take this value and either search in your code base for it and confirm that it was actually your code, or you can build up signatures for common extensions that inject stuff. So for example, for some reason, AdGuard seems to inject scripts into every single page you visit, and that's like, for example, counts 1 million of the noise reports, right? And there's like a really nice GitHub page from Nico3333FR that basically collects a lot of these signatures, and you can just use them to filter your results and, get some actually useful CSP reports. So with that, I'll hand over to Michele, who will talk about the tools we have developed to roll out CSP at scale, basically.
Awesome. So we have contributed to the content security policy specification. We made it better. We added some keywords. We changed some behavior in a backward-compatible way. We deployed it to hundreds of products serving billions of users. But it is very hard to scale at this scale, and it's very important to build some infrastructure and tools to support developers. So we developed, for example, an extension, which we call CSP Mitigator, which is aimed at helping developers prototype a policy by just installing an extension, going to a website, seeing what would break and what needs to be changed in a website to adopt strict CSP, which is our way of doing CSP, and also providing guidance, helping to make necessary changes. This is very useful because when you want to deploy to several products, you need to enable developers to prototype policies on their own. And we have a short demo here. So this is Google Finance. It's a product that does not have CSP yet, and is not CSP ready. This is mostly due to the fact that it has some legacy code and templating system, so it was not as easy to enable CSP here. So this could be seen as a pretty complex web application that a normal developer wants to add CSP on. So you have here a default strict CSP, and what you do, you click Start, and then you refresh the page. And then you see that there are some dotted red borders. These are the parts of the page that are triggering some CSP violations. And the green ones are inline event handlers or inline scripts. So we can play around a little bit, like news, we see the same. Then let's do to the stock screener. Oh, this is very bad. We see a lot of, let's play around a little bit. Here, there is an inline event handler. We can see the green border. And basically, when we are done playing around here, see, this was triggering with inline event handler. So it's not breaking functionality. So this is actually a report-only policy, right? It's not enforcing, so it's not breaking the functionality. It's allowing you to exercise the user interface, but it's at the same time even graphically showing you that there is something wrong and where. So here there is a small counter. I don't know if you can see it, but it's saying 280. So it doesn't look very promising. We stop, and we have here a report. We have here a report of script elements without announced attributes. So these kind of script blocks have to be announced, and they're not. So here, for example, we use some Google Tag Services, which is some analytics tools, and so on. Here we have customer service. Here we have inline event handlers and JavaScript URIs. Mostly they are on-click. See, there is an on-click here. We can inspect more and so on. And basically, there are some information, some suggestions, like no CSP nonce has been detected, you should add nonces. No strict dynamic has been detected, you should add it. So this is a very cool and quick way to prototype policies.
Yeah, credits for that actually go to David Ross. And then we also have CSP Evaluator. We presented that already last time. It's a very easy tool to just put in your CSP and get back a result of, you know, if the CSP is actually a good mitigation against XSS or not, because most whitelist-based policies are broken, but there's also a lot of things you can get wrong with nonce-based policies, right? So basically, this is how the mitigator looks like. You can paste in a policy here, or you just type something, right? Twitter.com, and it tries to fetch it for you. Doesn't always work, but often it does. And then you get the results, right? So for example, in this case, a whitelist-based policy is used, and a lot of hosts are whitelists that are known to host JSONP, and any of the red ones can be used to bypass the policy, right? If you take, for example, bugs.chromium.org, you will see that there are like no known bypasses for that one, right? And there's also like sample policies and even a Chrome extension, which basically does the same, but just evaluates the policy of every site and shows like a green or a red icon, depending if the site's policy is good or not. Yes.
Cool. So internally, we developed something, a tool we call CSP Frontend for visualizing CSP violation reports. So this is not a trivial task at all. I mean, from an infrastructural point of view, because there are so many, like 50 million per day, but mostly, as Lucas said earlier, because of the noise. Actually, the vast majority of the reports we receive are noise. And so it's very hard to have a signal-first view of what are breakages and what is just random extensions, adding random scripts to the markup. So we had to come up with some strategies, especially deduplication strategies, that, for example, leverage script sample, which is the extra bit of information for inline event handlers and inline scripts that we presented before, because that's actually the most important signal we have. The majority of the violations we receive are inline script violations, and we don't know much more if we don't have script sample. While deduplicating even across browsers, across pages, across domains, but grouping by script sample, it is a much more concise and useful view of reports. We implemented real-time filtering of violation report fields so that you can, for example, filter by a particular browser version, a particular violated directive, and you see basically all the charts and everything updating in real time. Again, it's a lot of data, it's gigabytes of data, so it's not trivial to make it work client-side. And of course, if you want to drill down and actually see the single reports, non-deduplicated, you can do that. You can do that, and you can investigate further. So here is how the CSP frontend looks like. At the top, you can see some filters. So, for example, you see some versions, browsers, violated directive, blocked URI, document URI, and there are some operators such as contains and so on. So it's a pretty advanced filtering system. Then there is a high-level view with some charts of like time charts or basically the violations by violated directives. Then the top blocked URIs. This can also help understanding a little bit what's going on. And then there is a more detailed view of violation, which we'll see better in the next slide. I hope you can read it. Yes, should be pretty readable. So basically, this is the aggressive deduplication view. You can see there are, this is the timestamp. This is the last document URI. This is spaces.google.com, for example. Here you can see, for example, a blocked URI that is pstatic.davebestdeals.com. So we don't source scripts from davebestdeals.com at Google, right? So this is probably an extension or some malware. And so we can safely ignore it. Here we have some Korean connect.facebook.com SDK. This is also probably an extension. Maybe add a like button to every page, something like that. Also here, donationtools.org. It's very likely not us. And here it's a common CDN, which we don't use by policy. So this is not us. So basically, this is all noise, right? The sample, you can see just here, an inline event handler. Actually, this is sent by Firefox, which is a little bit less fine-grained. So this script sample that they send is just telling us which inline event handler it is, but without the content of the inline event handler. Chrome with report sample would send the actual JavaScript that is there. And finally, we have some high-level tools that are at our, let's say, front-end server, which, I mean, it can be considered like a glorified reverse proxy. And we check for every HTML response we send out. And we check, for example, for regressions. Did we stop serving CSPs? Are we serving bad CSPs? Are we serving unexpected CSPs? And there are some alerting infrastructure, too. Also, we integrated this with the CSP evaluator so that we can check exactly what is a bad policy. Like, are we sending out a bad policy? Are some teams, for example, writing a CSP from scratch and sending out an ineffective policy without realizing? Then, thanks to this kind of monitoring, we are able to find out. So this was the engineering part, so what we built to support the growth of CSP at Google, and we hope to eventually open source some more tools. So from what we said, the mitigator is on the Chrome Web Store. It's a Chrome extension. You can go there and use it, and we actually really like if you did, and send us some feedback if you use it. Also the evaluator, there is a link on the slide. It's public. It's very nice. The front end is an internal tool. It has a lot of internal dependencies, so we can't just open source it right away. But we are considering open sourcing it. And now I'd like to talk about some recent non-space CSP bypasses and how we are dealing with them. So the first CSP bypass, actually non-space CSP bypass that we would like to talk about is basically if you just put script src nonce random and you have an injection, and in that injection you just put base href evil.com. And then you have a nonce script that has a relative source, such as x.js or foo/bar.js, and it is nonced. The problem here is that the attacker is rebasing nonce scripts to their own domain. So since we don't have a whitelist, but we are just relying on the blessing by the nonce, scripts will execute because they have a valid nonce. So here the fix is to not forget to restrict base URI. So base URI none or base URI self if we really need to set some base URI, base href / something, for example, as a shortcut. So a problem with base URI self is that in the pretty uncommon case in which you have a path-based open redirectors on your domains, these can be bypassed. So you might say, why should you have a path-based open redirector, such as, I don't know, like /redirect/evil.com/ something, right? So nothing in the query, just in the path, and the server basically redirects to evil.com. Why should you have that? Well, at Google we have, and it's called AMP, Accelerated Mobile Pages. So it was very problematic to use self at Google, so we often opted for none or for a deep path. This, right, and the credit for this bypass goes to Jack Massa. The second bypass is abusing the set tag of SVG for changing attributes of other elements. So basically in SVG, there is this concept of animatable tags. And there was a bug in Chromium that allowed to animate actually any tag, not just the animatable one. So this was really just a bug in Chromium. For example, it was not present in Firefox. So if you have an XSS and what you do, you enter the SVG context by doing SVG, and then you put a set tag that basically instructs the browser to modify the href attribute to data alert 1 in this case. And then you have a legitimate script that was not in an SVG context, but now it is because it is an enclosed, this is an enclosed SVG tag, right? So now this script tag is inside SVG content. Basically SVG says, okay, there is, let's animate this and change it to this. So this was fixed in Chrome 58. This was just a bug, but it allowed for a bypass. And credit goes to Eduardo Villanava for this. Now, this is a category of bypasses which are pretty interesting, in my opinion, and they are all related to stealing and reusing nonces. So the whole idea, the whole foundation of nonces is that they are one time, they are unique per page load, and it is hard to reuse them. So even if you are able to steal them somehow, exfiltrate them, well, you can't reuse them without triggering a server-side page reload, and thus the nonce has changed, right? So that's the idea. But how can you exfiltrate them in the first place? So you can do it with CSS3 selectors like this. So you force display block because of content. Well, this is a detail. The thing is, you have this operator which means begins with. So here you're selecting scripts that have a nonce attribute that begins with A. And then what you do, you override the content with record A, and then basically you exfiltrate character by character. And what you're able to do, you exfiltrate the nonce this way. So this alone, it doesn't give much, because you also have to reuse them, right? Anyway, we'll see that later. There is another way of stealing nonces, and it is via dangly markup attacks. Dangly markup attacks are actually nothing new. They are known for several years. They are somehow a little bit hard to exploit in the real world, because often they need very complex syntax. So for example, in this case, you have an injection and you inject a form and then an input and then a text area. So the text area is a like CData-like tag. So basically everything inside the text area is not parsed, and it's considered basically CData, so like text, unparsed text. And basically you are able to get this script tag as content of the text area. So you can exfiltrate it and post it to your evil.com form. Okay, this is the idea. But as I said, it's very hard to reuse the nonce, because in theory you have to inject a script with the nonce you just stolen, but in the same page, because you can't reload the page because the nonce would have changed, right? So you have to make the browser reload the original document without triggering a server-side reload. So this is very hard, and there are some very complicated edge cases with exploiting HTTP cache, which is like a server-side cache, or client-side caches, such as the back-forward cache, which is a DOM cache. It is the cache that allows the browser to keep, for example, the state of the filled-in forms when you hit back in the back button of the browser and you see that the form is still filled in. And up cache is also something a little bit exotic, so I won't go too much into detail. So one way is to have a frame and also inject a frame and have a history back. This would not trigger a reload. And then there are some very peculiar cases that have different preconditions and constraints. So for example, if you have an XSS due to data received by post message, and you are polling and you're waiting for a post message, you have an on message, and then you have a DOM XSS there, well, then the page would have been refreshed, right? So you would be able to reuse the nonce. And yeah, so same if you have an XHR and you're waiting on the reply from the SSI, from the XHR. So how do we mitigate these bypasses? So regarding the injection of base tags, well, the fix there is simply adding base URI none. And we did Google-wide, and we encourage everyone to restrict base URI if they use nonce-based policies. Replacing legitimate script SOC was a Chrome bug that was fixed, so that's all. Preventing exfiltrations of nonce is a little bit more tricky. And our solution, our mitigation, is to not expose the nonce to the DOM at all. So basically, during parsing, the browser would replace the attributes of scripts that have a nonce with replaced. So basically, this would keep the .nonce web IDL property, but would remove the attribute. This means that CSS selectors can no longer access the property, and nothing else really can access the property. What about dangly markup attacks? So dangly markup attacks are actually a long lingering problem in web security. They really have not much to do with CSP, because, for example, if you can exfiltrate part of the markup, you can exfiltrate very sensitive data. You can exfiltrate, PIIs. You can exfiltrate tokens. You can exfiltrate very bad things. But for using dangly markup attacks to bypass non-space CSPs, well, the precondition is that you need some kind of parser inserted thing, such as document write, to be exploitable. So this, for example, does not play very well with strict dynamic. If you use strict dynamic document write without, sorry about that, that was wrong. So basically, this is a pretty restrictive precondition. You need the document write pre-existing in the page, where you can inject your stealing nonce. And there is a proposal to forbid parser instances syncs at all, so to forbid, for example, document write and company. It is, well, it will have to be rolled out at opt-in because we are basically disabling JS APIs. But it is fully compatible with strict dynamic. So all the properties that have strict dynamic basically will have this extra protection for free. And furthermore, it would encourage best coding practices because document write is very bad. For example, inner HTML is very bad. They are bad for performance, they're bad for security. So you should not use them. We hope to be able to add this to the specification, maybe as an opt-in. We'll see. It depends also a lot on the industry support for this. So here I have a small demo on, thank you. So this is Google+. This is Google+. We have strict CSP on Google+. And as you can see, we have some script. And we'll, okay, so we do document, query selector all, script nonce. Well, let's just get the first one. Query selector script nonce. This means get the first script with a nonce attribute. I think I can zoom. Yes. So here it is. The nonce is replaced. So if I do get attribute nonce, it will say replaced. But if I access the JavaScript property, like .nonce, it will be there. And if I inspect the page source, okay, if I inspect the page source, we see the nonce was there. It was replaced at parsing time by the browser. Okay? So the idea is that CSS selector can no longer steal it because it's not in the DOM anymore.
And this is in Chrome Canary. So if you try this at home, you only will see this if you use like a dev or Canary version. But it hopefully hits beta soon. Yeah. Yeah.
Yes. Yeah, this is kind of a work in progress. We are pushing the last touches to it. We also had to extend it to style tags, for example. So the next category of bypasses, which is very interesting, and in my opinion, it goes a little bit beyond CSP. This is actually a very interesting research by some of our colleagues, which I think will be presented soon. The idea is that strict CSP protects against traditional XSS, like reflected XSS, the vast majority of DOM XSS. If you have powerful JavaScript frameworks, libraries, that have some kind of evil-like functionality using a non-script DOM element as a source, then you have a problem. You have a problem not really with non-space policies, but with strict dynamics. So we have a problem with automatically blessing script creation through JavaScript DOM API, such as create element script. And if you have unsafe eval, also that. I'll explain in more detail what it means. So if you have some library that parses, for example, let's say you have jQuery. In jQuery, you can call .html, and you can pass some HTML to assign some HTML to an element. You can pass a script. But as you know, if you pass script to .innerHTML, that does not work because it is parser inserted and the script does not trigger. So jQuery authors wanted to be as easy as possible to developers, make developers' life as easy as possible. So they said, well, if the developer is adding a script tag, so it's doing .html script alert1 script, well, he probably wants the script to execute. So what I do instead, I will not use innerHTML, but I will create element script. I will add .text of the parsed JavaScript, and then I will append it to the body, or I will eval it directly. So the problem here is that browsers are CSP aware, but libraries in general are not. So if your library is powerful enough to do some kind of JavaScript parsing and getting sources from non-script tags, for example, from a meta tag or from a, I don't know, like an attribute JS action or something, then you might need to patch your library to make it CSP aware and enforce, for example, nonce checking at runtime. So this is, for example, jQuery. This is an example from GitHub. So this is the global eval functions. The global eval method is called when a script is detected in a basically .html or .append or .replace with. So basically any DOM manipulation function that modifies the HTML of an element. So code is JavaScript, okay? It's already being parsed, and this is JavaScript. So we have indirect eval, so indirect is eval. We trim the code. If the code is there, we check that if there is use strict with offset 1 in the code, which is ECMAScript 6 strict mode, then let's not use eval, but create element script, populate the script with the code, and add it to the head. Well, to the parent node of the head. And then remove it. Okay, so this is pretty bad because this is a strict dynamic bypass. Because strict dynamic, so jQuery is nonced, right? So it's allowed execution. And this is dynamic script creation. Otherwise, it just evals it. So for eval, you need unsafe eval, which if you can avoid using it, putting it in the policy, of course, your policy will be better. Just to reiterate, this is not a nonce-based CSP bypass. It's a strict dynamic bypass, not a nonce-based. So with nonces, this would not run, and this will not run unless there is unsafe eval. How we patch jQuery at Google? We don't use jQuery at Google, but we use it for some marketing pages and some internal tools. And what we decide to do is to just neuter it by throwing an error. You should not be here. We actually did something before doing that. We added some reporting functionalities that sent a CSP violation report so that we could use our CSP frontend to actually see what's going on, find which products were using jQuery with this path, and then we just neutered the branch.
So wrapping up everything, get your questions ready. Basically, we discussed that the whitelist-based CSPs are broken by design, and usually you should not use them. There's only very few edge cases where they make sense. At Google, at least, like the nonces plus strict dynamic really heavily simplified the CSP rollout, and it is probably, also making lives of other developers a lot easier. Also very important to highlight here, like the CSP is not a silver bullet. It is like a defense and depth mechanism. And there are bypasses, but they usually have various preconditions that have to be met and constraints. So overall, CSP is still a very powerful mitigation, but you have to know how to use it. And with that, thanks for your attention. And feel free to ask like any questions if you have some.
Wow, thank you very much, Michaela and Lucas. Thank you. Any questions from the floor? Yes? Excellent.
Okay, so I've noticed in your slide you had like a CSP validator with the known bugs list, right?
Yes.
So I was wondering, do you guys have, or if you published maybe the list of how to exploit these known bugs? Because I noticed you have like a red exclamation mark that says that this is vulnerable to XSS using JSON-P endpoints or something.
So thanks for the question. So first, the CSP validator is open source, so you actually can copy it and reuse it. It comes with like a list of like, I don't know, 100 or 500 most common whitelist bypasses we extracted from the search index. Usually this list is enough to bypass most whitelist-based policies because like all the CDNs have the bypasses, right? And also the paper really describes in detail how these bypasses work and how you can find bypasses yourself, basically. It's not rocket science, it's just like JSON-P endpoints you have to find in the domain and fiddle in some the right parameters, and then that usually works.
So that, I mean, but the idea is that when you use a whitelist-based policies for script, you trust that that an attacker can't control what that origin sends out. So you are basically hoping that the origin, you're trusting the full origin. So if you have JSON-P that is basically a proxy for your content, you just do callback your code. That origin sends back arbitrary code, and then you bypass.
And that violates the first assumption that the origin is trusted, right? Yep.
There's one question over there first, and then.
Thanks for your talk. I'm looking forward to seeing the applications in the open source repositories. I was wondering if you also investigated other media types in your CSP, like Flash, JPEG, movies, and so on.
So Flash is a very interesting problem, and you're right, you can also use Flash to trigger XSS, and it is also a CSP bypass, but this is why we have object source none, which basically blocks all Flash content by default, right? So by setting object default source to none, we block Flash, and JPEG themselves, I mean, or images, they usually cannot trigger JavaScript, and if so, you probably have something that you would still have to put into a script tag, right? And at this point, the browser still prevents the script tag itself from executing.
Yes, the MIME sniffing problems that used to be in the past are not longer present, basically modern browsers that support CSP, and anyway, when there is a script, this is subject to script SRC. So even if you're able somehow to execute a script, it's subject to script SRC policy. It's at a lower level in the browser logic.
Oh, yes, thank you. The CSP evaluator, does it also perform multiple requests to validate if the nuance is actually regenerated each time instead of being a constant variable? Being constant?
The question was if it checks if the nonces, for example, are constant, if it does multiple requests?
If they're random enough?
Currently not. There's a feature request for it, but currently it only does one fetch and tries to get the policy. It's very simple, but this is definitely something we should be doing because this is a very important point. People kind of copy and paste the slides, right? And then they have a constant nonce. And I mean, yeah, it's very trivial to bypass something like that. And yeah, but
so
thanks.
when we decided to use random with R4 and D0M for the first time in our slides, we are presenting that I think 2 years or even more. Yeah, it's 2 years. We were saying in 1 or 2 years we are gonna like check the web if people are using random, like static random string in the nonce attributes. We haven't done it yet, but
we should probably.
We should just for
I'm
the
pretty sure
logs.
people copied the slide one-to-one.
So regarding your front end, you mentioned that there was 50 million amounts of noise, and then you kind of went through, here are some of the ways to reduce the noise by looking at common signatures. For the other meat of those 50 million, can you share some of the strategies you used to actually get rid of some of the not false positives, some of the actual reports?
So basically, you still try to group them by like the important fields, right? Like where do they come from which domain? And then maybe also by script sample. So you, in the end, you maybe end up with like 5 script sample lines, and then we usually take them and look into our internal code search and try to verify that this is actually code that is from us, right? And by that, we can very easily tell if this is something that is broken on our side. And we also take the same snippet often and search, just put in a Google search, and then sometimes you see pages with that or extensions, and then you know it's a false positive. So at this stage, it becomes a bit manual, right? But it's not so bad anymore because there is a couple of violation extensions that are very noisy, and as soon as you can filter them out, the data is much, much more actionable actually, right? But you're right, it is still some work left. And what we also do is we kind of keep monitoring the volume of these of these filtered results, right? And if they, for example, spike that could be a regression, and then we can alert on that, right? Because it could be that the developer from one day of the other like submits some code that has like, you know, inline JavaScript or inline event handlers, or it's like non-sync disabled or whatever, then we would immediately see a spike in the violations, right? And we could act on top of that. And yeah, I hope this answers the question to some extent.
Thank you. Any other questions from the floor? No? All right, great.
Thank you so much for
Thank you very much,
Goodbye.
Lucas, Michele.